to go ahead and try to solve this problem. You have a couple files you've opened. One of them is this Rhino file that has this little analysis here, and then there's a Grasshopper file that has a red component that we'll fix as we go, and then I'll talk about this stuff in a bit. Also, you have to make sure that you have in special folders components, you've dropped in the GH-Python2 file. Okay, so you also downloaded that. Drop that in like we did in the first workshop, and then restart Rhino. Any questions about that, please just raise your hand. Okay, so I'm just going to show you really quickly part of the problem, and this analysis sorts of I guess kind of shows it. Here I've kind of shown the modules and where they exist with a circle, and the kind of distance in the red lines that's necessary to set between those modules in order for the edges to align up appropriately. Maybe a little bit better explained over here where I left a little bit of a reveal. And you can see that the center points down here, are not aligned directly, right? There's an angle, and that angle happens to be around 4.715 degrees. It's not important to know why that is, because it's just an analysis that I found to be true. But the point is that because we have basically a kind of a non-standard grid. So we have two choices. We can organize these larger hexagons by moving their centers relative to one another, or we can rotate the module. And it turns out that rotating each one of the separate modules as opposed to rotating the organizational grid works pretty well. And we're going to use a little bit of scripting in order to do that, because without it, we're going to have a hard time actually organizing these as separate modules. It's quite easy to draw this pattern without the modularity. That's simple. But if you want to organize these sets into their own simple or their own discrete sets so that you can color them later, you need to be a little bit more considered about that. So the first thing we'll do is we'll actually just show kind of what this script does, but we're going to first open up the text file before we get into this. So type in Rhino, type in edit Python script, okay, and open that up. And by default, mine is just going to open right up because this is the last one that I've opened. You're going to have to go to File, Open, and navigate over to where this file is, and it's called hexagon_angle.4.715.py. It's the .py extension, so go ahead and open that up. And this is a fellow who wrote this code here. This is the credit, and I've kind of reworked it a little bit to make it work with Grasshopper. But this is not Grasshopper, right? So Python is its own programming language that works within Rhino using the Rhino Python, basically the kind of modified language that's called Rhino Python. And the other thing that we can do here is we can kind of input other ways of coding, and in this case, because this one was originally written with RhinoScript syntax, we've gone ahead and kind of imported that into this Python environment. I'm not going to get into the details of all of that, but just know that in here, what we're basically doing is setting some of the input parameters, and we're going to look at those as we run it. So go ahead, without getting too deep into this, go ahead and just hit the little green button up here, the one that says Start Debugging. That's basically running the script. So right away, it's going to disappear, and up at the command line, you're going to see specify center points. You can just click anywhere on screen, and I'm going to go over into our kind of our grid space, maybe over here, and click a point. And then the next parameter that it's asking you to input is the radial levels. You can leave that alone at 3, so just hit enter. The size of the hexagon, we can play with that a little bit if you like, but I'm going to leave it at 1, which is just 1 unit, whatever the file is set to. And the rotation angle of hexagons, we'll play with that in just a second. But go ahead and leave it at 0 for now. Okay, and you can see what happened on my screen is code comes back up, but just before that, it started drawing all my hexagons on, and you can kind of see the process play out, this kind of radial pattern play out. And it's going to draw it on the layer that I have active, which is the layer 5, which is the white layer. In your case, it'll probably be different. Yeah, so we've drawn a series of separate hexagons in this kind of pattern, which is very, very similar or identical to the pattern that we saw on the Santa Caterina. So we've got a pretty good start. And it turns out also that the number of small hexagons in each one of these modules is 37, including the center, and that's what we have our our parameter set to in the script. So it's actually producing this for us. Now, just to kind of demonstrate the problem, I'm going to join this. And you don't have to necessarily do this yourself. You can just follow along for a minute just to kind of give you some context. So I'm going to not join, but I'm going to group this. And I'm just going to copy and paste this stuff, right? Kind of thinking like that I might be able to build this overall modularity just by copying and pasting the hexagons, because you can do that with a typical hexagon. But you can see I'm already encountering an issue, right? I want to kind of put it here because that's its orthogonal direction right over, which would then give me a space up there, you know, to put the next one. But I can't, right? Because if I do that, I have a gap in between, right? And that's because it's not a straight edge. It's a serrated edge using the hex geometry. So I have to actually shift it in order to get it to nest into one another. So that's the first thing, right? So if I take now, let's close this out for a minute. Go to my layers, go to my red layer. This is the center point, and if I kind of drag a construction line over, you can see that I'm about 1/2 unit away to find that center line. Okay, so my analysis was simple. I just measured the angle in between this line and that line, which turns out to be around 4.715. And this works. I can copy this one now and fit it right into where we would expect it to go, right in here, and of course, we don't have any problems. The nesting plays out pretty well. Okay. But we're still having this kind of a shifted, we have a shifted set of modules. Just to draw another construction line out from the center, you can start to see that I'm creating a set of equilateral triangles between the hexagons. And that's good because any normal hexagon will also have that relationship between their centers. So really the only thing is this angle. Now, again, I could probably, using Grasshopper, I can script up a kind of a shifted triangular grid to organize all of these hexagon modules. But what I'm going to do instead is try something else out, which is to just simply rotate the module itself. All right, rotate every one of the components inside and see if that works. So I'm going to rerun the script, and you can join me if you like. So I'm going to go back to Edit Python script. And instead now I'm going to change an input. Right, I'm going to run it. I'll set my center point over here to start something new. Same level, same number of levels, same size hexagons. And this time, in the part where it says rotation angle, I'm going to type in 4.715. Okay, and hit enter. So it redrew it, and you can see now that it's at a slight angle. All right, so let me group that. And now let's see what happens if I try to align my centers. So I'm going to draw a construction line from the center out. I'm going to copy this over using one of these points, holding shift to see, you know, how that goes. And it looks like now I could just go straight over. I'm going to find that intersection point there, and my centers are now aligned. Okay, you can see it here. So there's my center point. It's aligned nicely. I can now draw a normal, let's say, or a regular triangular grid to organize all of my hexagons. And let's do one last test. And let's drop this in, and it should be just fine. Yeah. So in order to produce my tiling, I could use this script and its parameters that are available to us in order to do this. What I need to do is modify it so that it can input multiple points, and then I need to develop a kind of a ratio so that whatever I do to the distance between the triangle lengths, right? So as I scale this triangular grid, what will end up becoming a grid, everything else kind of updates, right? We can use Grasshopper for that, and that's what we're going to do. So we're going to show how we can kind of incorporate this Python script into a Grasshopper script in order to produce the kind of similar effect to the market. Okay. Okay, so that's the context. Let me open up Grasshopper again. It got hidden somewhere. Where is it? Oh, it's over here. Okay. All right. Just gonna make that a little bit bigger. Okay. And this stuff that we did before, I'm just gonna move that down. I want to keep it out of the way, and I'm gonna work in this space like we normally do in here. All right. So let's get going. As I said before, the first thing we want to do is we need that organizational grid. And this goes all the way back to last semester and in probably some of the themes that we looked at already this semester. But we need to start organizing our geometry and giving it a place to go. So I'm going to go back to the original part of the script over here and leave this where it is for now. And I'm going to, over in vector, I'm just going to grab one of the triangular grid components. And that, will start drawing a grid for us, as you can see here. And here's some of the inputs that I'm going to put in, and you can go ahead and follow along. I'm going to type in 10 for our spacing variable, and I'm going to label this. I'm going to right-click and just type in spacing variable. I'm going to try to keep myself organized on this one. Okay, so spacing variable. Oops, there we go. And that'll be going into the S input, because that'll set the kind of the scale of the triangle, right? And this is going to be a very important variable. Getting this wrong will mean that we'll have overlap in our hexagon modules, and we obviously don't want that. And then for the scope of this exercise, and obviously this is something you can change on your own, but for this one I'd like everyone to use these values, and I'll describe that why that is later. So I'm going to type in a couple of new panels here, and I'm going to just give this thing a scope basically of 8 units or not 8 units, but 8 triangles in one direction and 5 in the other. Okay, so 8, 5 is going to be our kind of breakdown here. All right. Okay. Now what we want out of this is not really the outlines. We don't necessarily need that. We need the points. And that's coming out here. So let's go ahead and turn off that preview, and I'm going to flatten the output of this because we don't need them to be nested in any sort of organization, but what we do have now is some overlapping points. Oh, you know what? Let me check something first. I think I might be wrong here. Hang on. Yeah, so these actually are my grid centers. I don't want these. I do not want these. I actually want the points at this location, right? Because that's actually at the end points of the triangle. That's what I need in order to get this hexagonal pattern to actually work. Because again, back to what we talked about before is hexagons and triangles have a direct relationship to one another in terms of setting the spacing and so on. So I'm going to turn that off, and I'm going to output my curves, and I'm going to find the endpoints of those by checking for discontinuities. So I'm going to go to Curve tab, and I'm going to grab this little discontinuity button here, component, and sorry, I'm going to go turn off these icons for you guys. There you go. Okay, so we've started to draw out, the corner points, if you will, of the triangles. But at the same time, I know that I have duplicates because these are polylines that are separate from one another. And now I have a series of 3 points here instead of just 1. And there's no reason for that, so I'm going to go ahead and flatten this. Output of P. And then I'm going to go over to Vector, and I'm going to find in the point box, I'm going to find the call duplicates component. And that's going to remove, now if I hover over this, right, I have 120 points at their discontinuities. Here now I only have, as an output, 30. All right, so it got rid of, so basically cut it into a third, and that makes sense because each triangle has 3 points. Okay, so we have our grid now that's going to that we're going to use to set up our hexagonal tiling system. Okay, so now let's have a look at I'm going to scroll over here to this red box, the thing that's throwing an error right now. And the only reason why it's throwing an error is because it has no inputs, okay? But this is a custom Python component that I created using the script that we looked at earlier. I'll show you where that is. That's in Maths in Python script. So by default, it looks like this. And obviously, you can make a series of edits to control what happens inside of this. So this is, again, it's extending the functionality of just what Grasshopper can do by allowing us to actually customize our own components. So in a way, we've created a little bit of a custom component here in order to do the thing that we want. And now, if you double-click on the word Python right in the center of the component there, it'll bring up an editor like this. And you're going to see that the code inside looks pretty similar to the one you saw before, but there are some key differences in that I didn't have to call the variables. Some of the variables at the beginning that are the inputs, like these here, these are just kind of taken in and understood. I'll show you that in a sec. There are other arrays and other variables that I left inside here that I think don't need to be changed, like how many edges and how many levels we're talking about. That does not have to change. The sizing of the hex and all of that will stay the same as a variable, but I can change certain inputs inside of it. And those are some of the inputs here, so I do have some control over this, and we'll exercise those later, and so on. The other thing is we have to kind of call and append the geometry in order to see it. That's something we don't have to do in the Python script that we looked at earlier. So there's ways of working with the components, basically kind of a box where stuff happens, and if you put input stuff in, you have to kind of call it to come out, right? And that's what these little guys are here. So you don't have to do anything here, just hit OK. And we'll just start playing around a little bit. I also have a series of solution states up here that I've saved, and I'm gonna talk about those in just a minute. But let's look at what we need. So we got to input points. Okay. We have to input a float, which is basically a number with the decimal of the edge length for each one of our small hexagons. We can control that. We can also control the rotation angle of the small hexagons, thereby affecting the overall rotation of the larger one. This is the kind of internal hexagon size. We can add, basically by changing this, we can add a little reveal, if you will, between each one of the, like a grout distance, for example, if you wanted to show that. I'll show you that too. And also the in-hex rotation. So we can actually not only kind of control the outer, the overall kind of pattern, how that's rotated, but also we can kind of further rotate the smaller ones in order to create a kind of a new pattern on the inside of the larger hex module. That will become clear when we start playing around. So the first thing is, let's just go ahead and drop in the points into here, because we know that that's our organizational point grid. And let's look at some of these. Let's just go with some of these options. Okay, this one is not necessary at the moment, but we can look at option A, for example. And you can take these and copy and paste them, and we'll use these to get started. All right, just gonna grab that somehow. Oh, it's having some trouble. Let's do that. Okay. And let's have a look. So let's pop these in order. So the edge length, oops, goofed up. Disconnect that. Edge length is something that we'll set in just a minute. I can take, this is my rotation angle like we looked at earlier. This is my kind of in-hex division, which is going to set the size, and overall in-hex rotation angle is 30, which will kind of make them sort of orthogonal to one another. Now all we got to do is kind of input an edge length, and for that I'm going to throw in this one here. Oh, that jumps the gun a little bit. Actually, start a new, just jump, go ahead and put a new panel in and just type in, I guess 0.93, I think works in this ratio. Go ahead and pop that in. So that should go gray. And again, sorry if you got confused there, but what I have is a series of inputs, 0.93 into the edge length, and as you can see here, these are my inputs for now. All right, and we can go ahead and just turn on the output here, and I'll put a curve parameter in over in parameters curve, just to kind of have a look at it. Now you can see on my screen what I've drawn, and centered along each one of those points that we input along the triangular grid. I can turn that on so we can look at it. Right, are now these kind of hexagonal modules that themselves are made up of 37 individual smaller hexagons. Okay, so it's working. The interesting thing is too is this little reveal in between, right? And I like this, as I like having some control over this, because actually I think it's a way to further clarify, especially in a representation like a drawing, you know, how this system works. I can change that. I can make it tighter if I'd like. As a matter of fact, I think if I turn this to 0.4, it's going to get real close. I can probably fine-tune this even further, you know, by maybe adding another, let's say, number to that. Yeah. And to get it dead on, I mean, you'd have to experiment a little bit. The thing that's interesting here is that it's hard to get that dead on, right? Because I'm actually modeling all these modules from the kind of the inside out, from the center point out, right? And it's a radial thing that happens. So here it's drawing a circle, subdividing it, putting hexagons, and it does it again, and it does it again. Okay. So it's kind of, so that's why this distance in between is critical. So this sets up a kind of logical way of thinking, and this is something I've been trying to introduce to you throughout the term. At the same time, we're extending what we can do with Grasshopper by actually drawing this using this script, because by default, none of the components in Grasshopper natively are going to do this. They're going to draw a hexagonal grid in a rectilinear boundary. Okay, and that's why this is very important to achieve the results we like. Okay. Now, I mentioned also that I want to put in a ratio, right? So something that, I'm going to turn this back to 9.3 on my screen just to, because I want to see that gap. Actually, it's helpful in these earlier phases. And now what I want to do is I want to make this input of the edge length, I want that to be parametric to this spacing variable. And the reason is that if I go ahead and change the sizing of my tiling, but I don't update the edge length, I'll either have an overlap or I'll have way too much space in between, which means I got to go back and manually change this one as well. And then it's just guesswork. I mean, that's fine, I guess, if you don't really have to make a lot of changes, but it's much better, especially if you have to share this file with collaborators, to just kind of reduce the amount of parameters you're working with. And we're going to set up a ratio for this, and let's work on it. So I'm going to grab a panel here. I'm going to type in 1, because I'm going to start setting up my ratio, 1 to something, okay? And the other end of that ratio is 10.54, and this is something that I just kind of discovered by analyzing the Santa Caterina pattern. And works in this example, okay? So 1 to 10.54 is my initial ratio. I'm going to try to convert this number relative to this one. So instead of 10.54, I'm going to say, okay, my variable here is 10. What does that value need to be? All right? Pretty simple process. Go to math. What we can do is multiply this first value, right? This is just basic arithmetic, by our first part of our ratio, okay? This is just basically what we're going to be, it's just cross multiplication is what we're going to end up doing. And then we're going to divide that result by the other end of our ratio here. And we can see the result now is 0.9487. Remember before we kind of modified that a little bit to get it closer? If we plug that result into the, into hex EL edge length, you can see now that I can hardly see where that break is occurring, and you can see that it is occurring a little bit here. But I mean, within the tolerances of any architecture project, that is very much acceptable, I'd have to say. I mean, that's a fraction, a tiny, tiny, tiny fraction of an inch, probably a couple thousandth of an inch. So it's pretty much dead on in my world. There you go. We've got a tight tiling. But let's say I wanted to control that offset. I mean, it's good to see it, right? All we got to do is just kind of subtract a little bit, a tiny little bit off of this value in order to control that. And I can make that a variable. So I'm gonna pop in a slider. And I'm going to make the extents of this slider very small. So I'm going to right click on it and go to edit. And I'm just going to change this to 0.075. Okay, very, very little. So it's going to go between 0 and 0.075. And I'm going to plug that into B, just do a little subtraction, and then go ahead and swap that out. And you can see now that I'm back. I have now that control again, right? And I can update this as I go. And I can kind of give this a little bit of a scalar input in order to increase or decrease the amount of reveal space between the modules. Maybe that's something that is important in the project. Okay, so we've set our ratio. That means if I change this, we can go ahead and play with it if you want. You can change this, and that ratio will update. The spacing proportional to the rest of the system will be intact. Okay, it's quite good. I'll leave it at 10 and keep going. Okay, so the next thing I'm going to introduce is solution states. Okay, and Grasshopper has a nice way of saving different kinds of states coming out of sliders, which allows you to very quickly go through results that you like, that you want to, let's say, demonstrate to your team or to yourself as you work on this. And you don't have to change the sliders in order to do it. You can actually save their values using Grasshopper and do it really quickly. So what I'm going to do for this is I'm going to change, because I already have a couple presets. Remember these up here? So let's look through and play with these a bit. Let's put in 0.010 for this one. That's basically this, okay? And I'm going to label this like I did here, module. It's kind of module offset, I'll call this, so I don't forget. And then what I'm going to do is I'm going to put in some new sliders here, and I'm going to mimic these values. All right, that came out of my option A. And I'm going to just mimic those values. So I'm going to go in here, and I'm going to make this slider that can go, I'm going to edit that again, make that a slider that can kind of reach, let's say, I guess 6 is probably fine here. Then I'm going to double click on it and change the value to 4.715. And I'm going to input that into my rotation angle to replace basically I'm just replacing this this little guy there, the panel, because these, unfortunately, you can't save the states to. Maybe you can. I haven't really tried that, but maybe you can make it multi-line data and do that. I don't really know. In this case, though, I'm just going to make them sliders because it's a little easier. All right, then I'm going to copy and paste this one, and going back up here, we know that we have a value of 2, so let's make that 2. Pop that into there. And then the last one to replace is this here, 30. And I'm going to make a new slider in this case and edit that out and make it anywhere between 0 and, let's say, or actually, you know what? I'm going to go a minimum of 15 and a maximum of 45, something like that. I think it'd be kind of cool. Because we know we need at least some angle. 0 wouldn't make any sense, and I'll show you that later. And I'm going to double click this and turn it to 30. All right. And replace that. Okay. So I have a solution here that's working, and maybe this is one that we want to share later. So I can put a little, I'm going to use my little center mouse button and put a group around that and call this A so that we remember that this is part of option A. Well, you know what? That's actually kind of silly because when we update the states, it'll just change that anyway. But I will at least put, I won't label it, but I'll at least put a little bubble around it so that, we know that those things are related. Okay, now to save that solution state before we go on and change it and to play with the results a little bit, you can go up to Solution up at the top of the Grasshopper screen, and underneath you're going to see the little Save State option in the menu. Now here it's going to say number slider, number slider. Yeah, these are the 4 number sliders that we want to actually save their states. So the exact number that's inside will be saved inside this little data base. We're going to call it option A. Okay, and you can go ahead and click OK. So now if you go back up to solution, we can see what happened. Now there's a few more options here now, and we can restore that state anytime we want because it's now available to us as an option. We can also delete it if we like. If we don't like it at all anymore, we can get rid of it. Now because it's already restored, we don't have to, this won't do anything other than show us what we already have. Let's make a couple of changes and let's play with our solution states. Okay. All right. So the next one, 0.051. Let's plug that in. And you're going to see some changes being made. So there's a larger offset. And we're going to kind of do something else with this part. So this time we're looking at a 5.25 as my rotation angle. And that's going to rotate things ever so slightly. I'm going to also now increase the spacing a bit between the small hexagons. Give those a little grout line in between. And now you can see we've got a little bit of an overlap. It's starting to reveal a couple issues actually. Not only the overlap, but also the fact that we're not actually drawing a center hexagon. And we're going to fix that in later steps. And then the last thing I want to update is based on this little roadmap here, I'm going to make this 20. Change my rotation a little bit. Okay. Let's make sure that's right. 0.51, 5.25, 2. I made my rotation angle 6 by accident. I need to change that to 5.25. There we go. So if you get everything just right and it's set like I've kind of had it here, you can see what I've done. And what I've done basically is put a little bit of a distance between every one of the hexagons, and I've rotated them a little bit to get a little bit of a little geometric pattern in let's say the grout that would be in between the tiles as we set them. So in and of themselves, the detail between each hexagon is now being kind of experimented with, right? So instead of just typical tiling, we now have an overall system which could still take on separate colors, and we'll get to that later, but we can't really see where the modules begin and end anymore. And we're also kind of shifting the relationship between the outer module shape and the inner tile geometry. And that's because we've rotated each one of these independently from its overall module, which is actually kind of nice. And later when we color things, you're going to see how that plays out. But now that we've got a state that's set, we can save this one as well. So we go to Solution, Save State, and we can now call this one Option B. Okay. All right. And we're going to do one more. Let's just go through and make that 026. And then we're going to update these as well. So this has to go back down to 4.715. This goes to 2.2 as my divisor. and this will be back to 30. All right, and what this one does is kind of something similar to the last one, except that it keeps everything pretty regular in terms of its hexagonal relationships. And again, we're going to fix that in just a second, so ignore it. But you can see now that it's just the hexagons that are expanded a little bit apart from one another, and they're expanded. Each module is also expanded away from themselves as modules to the same distance, more or less, at least by eye, between them. So the modules themselves are spaced to about the same spacing between each little individual unit. And again, that gives you the kind of effect of it being a continuous tiling, but we still have the data organized in the way that we want. You can see how it's coming out into these kind of separate chunks, right? And that's, I have 30 modules, 0 through 29 are their indices, and you can kind of see that there, okay? And when we go to, to get to the point of starting to color them, you'll see why that's useful. First things first, let's fix this little center problem. The script as it's set in here by default didn't actually draw that center one, but I added a little something to it in the end there. I kind of called it in its own function, and I just kind of added it as a center. Now, and it's coming out of this output here. All we got to do is kind of merge the two together, and I've already simplified that data. I'm going to get rid of this for now because we're going to end up replacing it with the next step. So let's go to Sets, Tree, Merge, and we can drop both of those in there and get rid of this D3 by zooming in. All right. And now we've got that center, right, that center hex now being kind of visualized for us and being drawn. And now my data is exactly the same, right? So it's organized right, but I have one more hexagon in there, and that's the 37th. Okay, that's pretty cool. All right, so we fixed one problem. Let's keep moving. The next thing is to start organizing this not only into its kind of color, its colored gradients, but also we're going to map it to a slightly more complex surface. Your file, I just realized that I didn't save all the things that I wanted to give you. Your file, by the time you're listening to this, will have a couple more components over here, and there'll be a surface, and there'll also be a what's called the random color generator. And I'm gonna give you guys both of those in this video right now. And again, you'll already have that in your script as you open it, or when you open it. But here's what those look like. All right, and we're gonna get to these things as we go, as we move forward. First things first, let's just test before we start mapping anything to a surface, let's just test the color generator. All right, and this is a little cluster that I built. If you double click on it, you can see what's inside. It's just a way of sharing, let's say, a larger chunk of code with folks. I didn't lock it down. You can edit it if you like. I'm going to just discard and close on that. You don't have to change anything inside here. It works just fine. Let's put a couple inputs into this before we assign it to geometry. So here I'm going to, again, this is similar to what we did in the last, it's the same set of components that we used in the last exercise when we started coloring the bricks or the dots for the Diong. So we're going to kind of develop two random color values. This is my seed value. I'm just going to make it 6 for now. We can change it. The count is actually going to have to come from how many items we're trying to color, and we'll get that in a second. And then the alpha value is just something I like to add because it looks better. You don't get any of that gloss coming off the Rhino kind of lights by default. So I'm going to make that 10, give it a little bit of transparency. Now, the count is important. What I need to do is measure how many things I'm trying to count. And I'm going to use this in order to do that because I have that number of modules. And this, in a way, counts the modules because it puts one center hex for each module. So it does, in a way, count the modules. So I'm going to go to Sets. I'm going to grab this list length component, plug that in like so, and then flatten this. Flatten that input. Right-click, flatten that input. That's going to give me a number of 30, and that makes sense. And that's my count. All right. And now coming out of this, I get a nice matching. I have data that's matching the data that's coming out of my merge. Right? If you look at the indices, 0 through 29, 0 through 29, then we can start matching up these values. In order to really see their colors, we need to use the custom display component, like you might remember. And we can go ahead and drop that in like so. We can turn off this merge so we don't get any kind of overlap, and then use these to color everything. And now if I zoom out, you're going to see that we've kind of placed a random color using those similar values that I used before in the last exercise to each one of these modules. So it's demonstrating how the script is actually working. And we're getting a similar effect. Even though we're using different colors, we're getting a very similar effect to the market. Okay, so we're in good shape in terms of data and in terms of this geometric relationships. Things are working very nicely. And instead of coloring the curves, what we can do actually is draw a planar surface through these, right, a boundary surface. And I grab that up in the surface tab, freeform, boundary surface, okay. And we can color those instead and turn off the boundary surface component in terms of its preview so we can actually get a better look at this, okay. And we're going to change the colors a little bit later, but for now I think this is good feedback so we know that things are working. Okay, cool. So the next thing is to then map it to a surface. And I'm going to go to my perspective view for this. Okay. And I'm going to just reveal the surface that we're going to map it to. And this is just a quick thing I drew in Rhino. All it is a kind of it's kind of arched on one side, that low, and arched high on the other, and then just a straight line in between. So it's an inflected surface, and it's good enough to test whether or not this geometry can be mapped. This is not parametric, meaning that I modeled this relative to the kind of general size and boundary of my hexagonal pattern. But if I go and change that in the beginning of the script, for example in here, the surface won't update, and that's not hard to do. Maybe you can experiment with that on your own. But for now, let's keep it where it is, and we're just gonna kind of map these things directly to it. All right, so I could turn that surface off. I don't actually need to see it. I just wanted to show it to you so that you know what we're doing. Yes. Okay. What we're going to actually end up mapping is not the surfaces themselves. We're going to end up mapping the curves, but we're going to use the surfaces as a way to engage with the next component. And let's look at that. I'm going to give myself a little bit of workspace here, okay? That's all I'm doing right now. Giving myself a little bit of room to work. All right, so we have a surface. What we're going to use is the map, this kind of surface mapping component, map to surface. I can't remember where this is. I think it's in transform. Yeah, okay, so it's transform map, morph map to surface, all right. And the few inputs it needs, first of all, are the curves. Secondly, the base surface for initial coordinate space, and our surface target. Now, a couple of these we already know. We know we've got the target. Know that. We also have the curves, okay? And you want to make sure you don't change that data structure. That's important. So we leave it at the chain link line there, right? Now the only thing we need is to kind of reference the coordinate space that all those curves are on. And there's an easy way to do that. Just go to double click. I don't remember where this is, but double click and just type in bounding. You can find the bounding box component, okay? And it says down here per object. Right click on that and turn it to union. And then what we're putting a little box around basically is the curves, or sorry, the surfaces. I guess you could also use the curves. I suppose it doesn't really matter that much. But anyway, maybe not. I haven't experimented, but I know that this works. So from the boundary surfaces that we created before, we're putting basically a kind of set of union boxes around, in this case, each one of the modules. But we want to change that so that we're not running into any problems. So actually, an easy way to do that is to just flatten this. And now we're basically creating one single box around our entire system. That's what we wanted. You don't have to look at that. You could turn that preview off, but we can use that first output, the top B, and drop that right into our surface input here, or source input, I should say, sorry. And right away, you should be seeing this, which is just a direct mapping of that geometry that was below, directly above, and up to the surface. And now we're giving it a bit of curvature, right? You could use a similar process, I think, to try to accommodate the Santa Caterina geometry as well. And instead of now, then we can take all of these curves here, and we could we can color these as well if we make surfaces through them. But the question is, how do we make the surfaces? Let's do this. Go to surface, and let's see if we can make a boundary surface out of these. Okay. And I'm going to just plug that in. Now, it's going to stay orange and get confused because only, it turns out, in my case, 1, 2, 3, 4, 5, 6, 7, 8 of those curves are actually planar. And that's happening right around the kind of center of the surface. Sort of makes sense, right? The rest of them are actually twisted in space. They're not planar. So you might remember from the first exercise, we went through a process of fixing that. Those of you who did I suppose it was the Smithsonian exercise, will be a little bit familiar with the next step. So let's go about doing it. So I've got my curves here. I want to find their center point. I'm going to go to curve. You see this little polygon center component. I'll grab that. That's going to give me all my center points. I'm going to turn that off because it gets a little confusing. I'm just going to use this as a way to, I'm going to move that. The next thing is now to map these points to the surface itself so I can get those UV values. And I'm going to hold shift and grab a couple components like that. So surface closest and evaluate. And if I hold shift, I can grab more components, 1, 2, 3, 4 components at a time, and then just drop them in together. First thing I got to do is do the surface closest point. So the points that I want to kind of force to interact with the surface are these centers. I can then grab this surface here as my input. Okay, and you're going to see basically a repeating of these points, but now with new data. That's the UVP, and then we can plug that into the UV of evaluate using, of course, the same input of that kind of surface that we're mapping to. And now I've got the output here that's critical are the frames, right? These are my perpendicular frames to each one of those points relative to the curvature. And I'm going to continue moving this stuff back because I'm, again, just working through and giving myself some more space as I go. Okay. And now the question is basically projecting all of these points, all of the curves, I should say, to these frames to make them flat. Because the frame has no choice but to be planar. That's how frames work. Pop that up there, make it a little neater. Okay, we can go to vector. Is it in vector? Don't remember. It's not. It might be in transform. Let's go to there for a minute. Yeah. So transform, affine, project. The first one there. Just project onto a plane. And our planes are our frames, right? So F goes into the P input here, and then our geometry that we're projecting is our curves. And you're going to hardly see a difference. I guess if you keep that selected for a minute, you can kind of see how the red is deviating a little bit from the green there, and that's basically all we've done. We just had to shift everything ever so slightly to make it planar so that we can represent this right. And I'm going to turn off the original these mapped curves because they're old now, and then I should now be able to draw my boundary surface. My boundary surfaces like so. And it seems to be working. So now all of these new curves are now planar. And I've now drawn a new set of surfaces through them. And I can use this to preview, turn that boundary off, and I've basically shifted everything from the 2D plane up to this 3-dimensional curved geometry here. Okay? So we're getting pretty close to wrapping this up, and there was just one other thing that I wanted to do. But before I do that, let's play with some of our parameters that we had before. Here, I have a solution state that I've got plugged in, which is all these values. Let's go up to solution and restore a different state. Oh, by the way, we forgot to save this one, so let's call this. I'm going to save that as option C before I change it. Okay, so that's been saved as option C, and now I can go to restore that option A. And it'll take a minute, but it updates. And you can see now that these smaller hexes are touching one another at their seams, but I have a larger reveal between the modules. I can display a different state, B. That was the rotation one. Very quickly. And if I want to go back to C, same process. Okay. Cool. I'm going to leave that one on. I kind of like this one. I think it's the most accurate to the architecture that we're looking at. And the other thing I'm going to do now is I'm going to get rid of this random color generator because I use this as a way to prototype. I think it's a good prototyping tool. But I'm going to make the colored variation now. We could actually map this to a surface like we did last week, or I'll introduce you to another way of thinking about adding color to this, which is to make it related to the height of each one of these center points of each one of the smaller modules within the module itself. So we're going to extract their z value, and we're going to place a color on that z value within each one of these independent modules to get a kind of an interesting color variation that doesn't go from here and all the way to there, but it exists inside of each one of these modules, and you get a kind of an interesting effect out of that overall. So let's start that, and we can leave this alone for now. We'll end up replacing that S input in just a second. So the question is now is what data are we looking at? And we're looking at this. Remember this these center points, right? So it's all the center points coming out of the polygon center component, and we can go to vector deconstruct point, right? So deconstruct point, so that CV output goes into there. And I'm going to put it up here to keep things organized, and we're going to be basically using this data coming out here, the Z data. I need to know a few things about it before I get into my gradient colors. I got to go to math. I got to figure out its min-max bounds, okay, like this. And I also need to deconstruct this domain so that I can break that down into two separate parts, right, start and end. All right. Now we can go over to parameters and grab this gradient sample, color gradient component. And by default, it's these pinks to reds. Right-clicking on it will allow you to pick through some presets. You can also customize this on your own. I'll show you that in a minute. But here, let's just choose the green, the dark green to light green preset. And let's put in the S and E values. So S into L0 and E into L1. And the values we're actually going to use to operate are the actual original values, right? So the Z values coming out. And that's going to be our T input. So we're basically, within these boundaries, we're finding a value, and we're going to place it relative to these colors from the spectrum of very low to higher, right? And that's the start and end boundaries. The only thing left to do now is put a little transparency to it, and to do that, I'll actually, you don't have to do this, but it's something that I like to do. I'm going to go to sets. I'm going to go to concatenate over in the text box there, and I'm going to pop this stuff in, because if you look at the data, it's actually just RGB values, right? Kind of like what we, oops, looks like I may have, there we go. Careful with the way you do there. Anyway, it's just RGB values, comma separated. All I got to do is just add another comma and a value to this to change its alpha value. And I'm going to use a panel for that, and I'm going to type in comma 110, and I'm going to add that little text chunk to my RGB values. You can see that here now. I just added that comma 110. And you can drop that into your color previewer. And yeah, check it out. So now what we have is, and I guess it's maybe better on this side for some reason. In my screen, Rhino has all these surfaces flipped. Anyway, you can kind of see now that per component, you're getting a different gradient in each one. So per module, I should say. So the lowest in Z value is going to be dark. And as it goes up to the highest, it'll start to lighten up a little bit. And you get a pretty cool effect out of that, I think, overall, if we look at the top view. You know, you get these dark values that are kind of almost diagonally being drawn through, and the light values being drawn in the opposite direction. And that's just due to the curvature of the surface. So if you were to change the surface geometry, this pattern would update. So the color pattern would update. So the colors are related directly to the form of the canopy, I guess, if you will. Also, again, you know, you can experiment with trying to incorporate some of the stuff we did last week, trying to read an image into this. It's really just a similar process, except this time you're using data sets instead of, you know, individual data points. Okay. I think that pretty much wraps us up. What I'm going to do, again, just to kind of play around, is demonstrate my solution states, just to kind of see how if that changes my colors at all. I don't know if it will too much, but let's go to B. Yeah, colors are more or less maintained, but the pattern changes, and everything is very happy. Everything works very clean. And now I've got 3 solutions to this architectural condition, if you will, that I can demonstrate very quickly on the fly to my audience. Okay. And that is all for this one. Thank you.